I'll start with a brief overview of the auto solver. It is a Matheuristic to solve the RIP. It was first implemented in DIMACS et al. 2020, and we extended this work to the competition. It implements on iOS RVND combined with the Network Simplex to run the exact part. It applies a collection of neighborhoods to explore the search space. The routing cost is calculated in constant time, and the optimal inventory is calculated using the Network Simplex. So here is the framework, the iOS that we are using. We start with a constructive heuristic. We use the two-phase algorithm from Alvarez, Monari, and Morabito. It is it's the constructive. It selects for each period a set of customers that must be attended at this period, or not, it will be stuck out. And a second set with customers that are good candidates to be attended. With these two sets of customers, we can create the routings. We are using a CVRP constructive heuristic here. It's by Subramanian 2012. And with the routings, we can calculate the deliveries using the Network Simplex. Together, we create the solution, and we do this a couple of times, varying the radial demand and lookahead parameter that are used to calculate the good candidates to be attended at this period. Next, the perturbation phase, we just choose a random neighborhood. And using a simulated annealing, we accept or not the movement, and we can do this up to 15 interactions. And during the perturbation, does not allow moves to infeasible solutions. The local search, as I said, it's RVND. We walk in the neighborhoods. First, we randomize the neighborhood list. And for each neighborhood we do a local search, we are doing a full search with first improvement strategy. And we do this until we cannot improve it anymore. During the local search, we have an indirect solution representation. For example, one solution like this, we have this solution representation. We are just representing the routings for each period and for each vehicle. And we have to decode this routing to the deliveries. And we are doing this using reducing to the mean cost flow problem. These are the neighborhoods that we are using in the local search. We have the insert, that we insert a customer in a route in a period. The remove, that will remove a customer from a period. The relocate move, that will remove a customer from one route to another route. This can be done across periods. The swap movement, that will just swap two customers in different routes. The shift, it will shift the customer in one position. And the reverse, that is the two-up movement. Finally, the acceptance criteria, we are doing the simulated annealing. And we choose temperatures, initial temperatures and the final temperatures, and the rate to decrease the temperature in a way that we can run this 500 times. And we start accepting solutions. It starts accepting solutions 20% worst with 20% of the probability. And then at the end, it accepts solutions 1% worse with 1% of probability. So then we got the best solution, but for the competition, we restart the solution till the maximum time reached. Now I'll talk about the mean cost flow problem. The reduction to this problem is not something new. And I will show how to model the inventory using the mean cost flow. Supposing that we have this solution, we start with the depot. It will supply a flow equals to the initial inventory and the current supply from this period. Since we have, in this example, 2 vehicles, we have new 2 nodes demanding 0. And to modeling the vehicle capacity, we connect this depot with the vehicles by an arc with cost 0 and with an arc capacity of the same capacity that's the vehicle. Then we have 1 node for each customers demanding the demands of the period. To model a route, we connect the vehicle with the customers, and the cost to delivery, in this case, the cost is 0, and the maximum capacity is infinite. We are guaranteed the capacity of the vehicle in the first arc here. Next, we can do this for other routes. Adding a new period, we just duplicate the nodes, demands the same amount of flow and supplying what the data pot is supplying this period. And here we model the inventory. Well, the amount of flow that one customer will pass to another period, the cost will be the arc cost will be the same as the inventory cost, and we can just pass the maximum, that is the amount of the maximum of this inventory node. We do this for the other routes and through the other periods. And finally, we create a new artificial vertex that demands the difference between the total supply and the total demand. Solving this inventory can take up to 65% of the running time. And then we got these research questions: if we can speed up this inventory calculation and still be optimal, and if we can use a previous solution to compute another solution. And how we can speed up. First, I will give just a brief review of the primal network simplex. And the network simplex, the algorithm that we use to solve the mean cost flows. We have 3 sets. One set T is the spanning tree. It is the basis of the solution. The other 2 sets L contain arcs with flow 0, and U contains arcs with flow equals to the capacities. They are out of the basis. And since we are trying to getting new arcs to the base and leaving and removing arcs to the bases, we have to calculate the reduced cost of each arcs. And we can do this calculating the dual variable for each node. So one iteration will be find a good enter arc to the base and a leaving arc to the base. Answering the question, can we use one solution to compute another? Well, usually any change in the solution would require executing the entire algorithm again, because some arcs may have been introduced or removed. Arc capacities may have changed. Node supplies may have been modified. The maximum flow may have changed, or the arc costs may have changed. But all items except item 5 imply structural changes on the graph. Can we propose a new model that avoids these changes? Yeah, we proposed a new model for this, a network model that reflects every possible solution on the same instance, on the same graph. And that's how we did. We have this solution, and as I said, we modeled the route, connecting the vehicle with the correct customer that will be attended. And now we create new arcs to every other customer that's not to be attended by this vehicle. But here we use a cost equal to infinity. So the flow will not choose this path. And we do this for all periods. And why does it work? The arcs will not, there is not new arcs introducing or removing. The arc capacity is still the same because the constraints are the same. The node supplies is not modified. The maximum flow will not be changed. The only change are the arc costs. And that's how we deal with it. And how we did, it's quite simple. We initialize the graph. We run a first time without any route. And for each new solution during our local search, before run the network simplex, we update the arc costs, only the vehicle to customers arcs, and we update the dual variable in a simple way that we go through all the spanning tree, updating the dual variable. That will be necessary to calculate the reduced cost and then to find the entering and the leaving arc. This result was pre-competition, was comparing the small instance with the fast flow and without, where we have to rebuild all the graph. And you can see that we improved a lot because this is how percent of the time, how much faster we are. For the competition, we use 3 new improvements. We are now just updating costs from the change arcs. We keep track of them. And during the checking to which arcs we need to enter in the spanning tree, we also keep track of which arcs should not leave, and we avoid to check them. And for the large instance, we avoid to run the network simplex if the route solution is some percentage worst. We did experimental results. We implemented it in C++, and to network simplex, we are using the solver Lemon. It's an open library. Our execution was give us 32 minutes of execution following the competition rule. And we got the 4th place. And yeah, we are close to the 3rd place. And the conclusion is that we proposed the Matheuristic to solve this RP variant. We provide a network model that allows hot start and critically speed up the computation of new inventory costs. The modifications enable 10 times fast running times, and the results show that computed the impact of change in the routes of the inventory enables find better solutions. That's the references, and thank you.